Hi, and welcome back. It's great to see that we're into a stage where we need to start thinking about the mistakes that are part of our process as we go through in science. Now, I've made this up deliberately to make sure that we have this understanding of what is going on and what we must do. All right, let's look at it. Whenever we are doing something, there is a high probability that we will make a mistake. That's just part of life. And we tend to find that our mistakes rely upon what we do with that mistake. Now, in science, we try to say that, yes, mistakes are there, but let's make allowances for them. And it's more about what we're going to do in our subsequent session on uncertainty. And we acknowledge that there is some uncertainty and there'll probably be some errors in measurement in our results, in our data. But that doesn't mean our data is useless. So let's have a look at what we're going to do here. First of all, let's make sure that we remember that learning is basically about trying something, or the scientific method, if you like, is also about trying something, coming up with an idea, saying, let's test this out and let's see what goes on. There is no guarantee we are going to prove something right. That's what we're trying to do, is maybe reduce the amount of options that are there. So we have to make the little bit of a jump in our mind to say that, okay, it's okay, we are going to make mistakes and there are going to be inaccuracies in our data. But if we look after it properly, then it is still reliable and still useful. So this only applies if we do not do anything about it. And you're going to have to do this in your subsequent reports in years 10, 11, 12 and 13. So it's a good idea if we have some idea what's going on. I'm just going to change to a different pointer. I think we'll go to full-on Jedi today. Alright, so let's see what's going on. So there are two types of mistakes basically. One type of mistake involves us making mistakes because we don't do things accurately or properly. We use the wrong equipment, do the wrong job, things like this. And you've got to remember that we should learn from this. So any time your teacher gives you feedback, they're saying, righto, these are the mistakes, how about we try to lessen them? It's not that we're going to ever get rid of errors. It's a simple matter, we want to make them okay so that our results are still meaningful. So when we're doing this, it's okay if we make mistakes, but then we try to fix it up. And you'll notice that in your BC criteria, there is a section on reflecting, and that is where this comes in. The reflection acknowledges that you've made a mistake and how you've gone about trying to fix it up, or how you've gone about trying to lessen the effect. Right, one common mistake we make is we don't do correct gathering of data, especially with analog things. Analog things look like this, right? So little marks for us to interpret. Now that means that somewhere in our brain we've got to interpret what we see and then give a value. And if we're doing this, it's highly likely that we're going to be out because we're going to be guessing. At some stage we'll be guessing about our values. Now it becomes even worse if we're a bit not so good at doing our measurements. We know that to get a correct and accurate measurement, our ISO level should be level with the meniscus in this case. If it's above, then we're going to be reading high. If it's below, we're going to be reading low. So it's most important that we try to always do the right thing in terms of gathering data. And this is one of the biggest sources of errors in any lab work. And I don't care if it's by a Nobel laureate or a Year 7 person at CIS. We are still doing this. Alright, so what is the problem? The problem is that our results become scattered. So there is a big range in our results from the lowest result we get to the highest result we get for a particular trial. So how do we get about this? This is, by the way, referred to as precision. When we're talking about precision of your data, it's how close they are together. And that is something you should always talk about also in your conclusion. I would expect you to say, yes, my results are quite precise because the range between highest and lowest values is small or quite small. As that range becomes larger, then of course our precision drops. So what do we do to try to make up for our mistakes? Well, the classic thing is we've taught you all the way from Year 7 to do multiple trials and then average the value. The average value is going to be closer to the real value. Alright, so that means that maybe this one is closer than the top one or the bottom one. Now, the more trials you do, the more precise you will become, because you will get a whole heap of values and it'll give you a much better idea. Now, your teacher might have also talked about the fact that you can have these things, outliers. They're values that don't really fit the group. They're a long way from, you might have some points here. I'm just going to change my colour. You might have points like this and then here. These are all close together. This one is a long way away. So it's highly likely, because I've got those 4 points there together, they're somewhere near where the real value would be. This one is called an outlier. So what we should do is to remove it from our calculations. Only use these ones, only use the ones closer. And that will give us a much more precise and more reliable data as well. So there are two things we can do, right, to help us with this. And we encourage you to do them all the time. The first thing is to make sure you do multiple trials. The more trials you do, the more precise you're going to end up. If you have outliers, remove them. So they should be removed from calculations. That includes your average. What's the point in saying this value here is an outlier and then still using it? That doesn't sort of make sense, does it? So this is what we want you to do from now on. Think about these things. Some of you at this stage are able to identify outliers, but you're not quite sure what to do from there. So here's where we move on. Right, the other common one is we don't set up properly. We're in a rush. I know, you get into a class, you want to get things done. So you come in and you say, right, I'm just going to put my thing on here and set it out. We don't check to see if that's reading 0 when there's nothing on there. That's called calibrating. Now, as you start to use data loggers, and you'll be using a lot more data loggers in the next few years, it's important that if you must, or if it is available for you to do it, you calibrate things. Now, for our temperature probes, that doesn't seem to be a problem. But if we're using a pH probe, you must calculate, or you must calibrate, sorry, and you must use buffer solutions. Now, these solutions are of an exact pH. Okay, so they have the exact pH. So if I put the probe in there, it should be exactly whatever it is. Now, normally when we're calibrating something like a pH probe, we use a pH of 4, we use an acidic one, a low pH one, and a higher pH one. Not like 2 and 1, but we maybe 4 and maybe 10, something like that. Now, if we calibrate against both of them, it means our results are going to be closer to the real results. Of course, what actually goes on with with our calibration, what we do is we push our numbers. Let's say that's our numbers for our real. That's the real value there. What we do with ours is we have the same sort of numbers, but we just move it down here, above or below the real value. And that's what it says about affecting the accuracy. Now, basically it's going to mean that all your results are going to have the same inherent inaccuracy. I said inaccuracy there, so it's error. Right, so if we do multiple trials, all we do is do the same thing over and over again. We make the same mistake over and over again. So our results stay here. This is what we're actually finding. So it's not really near the real result. So you don't choose it. So the best way of doing this is to make sure that you calibrate properly. So it's one of the things you need to get in practice of doing. Now, we actually give these things names, and you will hear them and you'll see them, and you should copy them. Whenever you're talking about these sort of errors over here involving us, our people errors, not doing things properly, right? They're called random errors. And every time we make a random error, it adds up. So the more we make, the bigger our total error is. Then if we don't do something here, we have to add this to it as well. I mean, you're going to find out in a subsequent lesson about how we must add and how we calculate errors and how we must show them in our final conclusions. And it's really important we do this and acknowledge our errors and things like that. Now, in a future lesson, I'm going to be talking about a thing called an uncertainty. Now, uncertainties are errors in the equipment we use, if you like, and you'll find them as plus or minus a value. So it might be 1 ml. This is an example only. So your uncertainty in your reading is always going to be plus or minus one of these. Now, if we're making 10, 15, 20 different readings, then it soon very quickly adds up. In a subsequent lesson, I will teach you how to calculate uncertainties. Right, that is our introduction to errors. You are expected to be able to start to use this from next year. So when you're in year 10, year 11, or year 12, or year 13, you are expected to be talking about your errors in your reflections, and you are supposed to be talking about your errors and showing your errors and uncertainties in your data tables, and you are also expected to use your uncertainties to show the range of the real value of your results. But again, that's another story.